Alright, so we're going to start where I left off right before spring break. So this is going to be online. Alright, so we were talking about the stellar classification. These are the designations. The main thing to remember is that O stars are really hot. They're the hottest of all the stars, and then the M stars are the coolest. There's actually a couple of stars, classifications after M, that came around a little bit later. We'll look into those a little later. All right, so another thing is to remember our star is a G-type star. The Sun is a G-type star. So I think I did an example of using the Doppler shift. This is the equation for the Doppler shift. It's delta lambda over, it should say lambda naught, which lambda naught is the wavelength in the laboratory, and then lambda is the wavelength of the object that's moving, and of course c is the speed of light and v is the relative velocity. All right, I'm going to do examples of these. And make a video for that as well. All right, so the main thing to remember is this value is positive if the object is moving away from us. If it's redshift, what we call redshifted, and then this is negative if it's moving towards us. That's called blue shifted. All right, so. So, another thing to remember is not only can we tell whether how fast something is moving, we can also tell whether it's moving towards us or away from us. All right, so all right. So let's talk a little bit about binary stars. These are stars that orbit each other. I think I talked a little bit about this last time, right before the spring break. About approximately 40%, a little less than half the stars in our own galaxy have companions, sometimes more than one. Like, for example, the Alpha Centauri system, which is the next star system over from the Sun, is a trinary system. There's actually 3 stars: Alpha Centauri, Beta Centauri, and another star called Proxima Centauri, which is a little bit closer than the other two, just slightly closer than the Alpha and the Beta star. Anyhow, all right. So, and we've known about binary stars for a long time. I would say probably the last at least 175 years we've had telescopes powerful enough to see some of the closer binary stars, these so-called visual binary stars. And remember, these are 2 stars that are actually orbiting each other, not 2 stars that just happen to be, close to each other in our own field of view, right? I mean, there's stars that are really near. You look up at the night sky, 2 stars might look like they're really close to each other, but they might be, many. Hundreds and hundreds and maybe even thousands of light years apart. These are stars that are really close to each other and even orbit a common center of mass. All right. Let's see. So one of the things that we can do with these binary stars, or with some of them, in fact, what are called the eclipsing binaries, that should be. Okay, let me cover this as well. So one of the things that you can do is using the original Kepler's third law, but what I call this equation is Kepler's third law for combined mass, where you get the mass, little m plus big M, which is just 2 different stars. And these are in what are called solar units. In other words, some number times the mass of the Sun. If the number is greater than 1, then it's greater than the mass of the sun. If it's less than 1, it's less. P is the period, of course, and that's in seconds, and A is of course the the distance between the stars in astronomical units. So there's a little example. Here's 2 stars that are orbiting each other that are 10 years. The period is 10 years apart. They average a distance of about 6 AU, and so we use this Kepler's third law for combined mass, and we get 2.16 times the mass of the sun. The M with a circle in it, circle as the subscript with a little dot in the middle, indicates the sun. So I usually write M sub sun. All right. Most stars, as it says, have a range anywhere from about 1/10 the mass of the sun to 30 times the mass of the sun. But just keep in mind, this equation only gives us the combined mass. It doesn't tell us what one individual star is. It tells us what that binary system, what the mass of the entire binary system is. So, in some sense, it's useful. Let me go back to it. It's useful, but we would really want to know what the individual mass is. This is what I was thinking about just a moment ago. So there's a class of binary stars, a very special class of binary stars, where the stars will actually, from our vantage point, from our viewpoint out into the Milky Way, will actually pass over each other. So sometimes the stars are orbiting each other, but they're going perpendicular to our line of sight, and so we never see them eclipsing. So these particular stars are what are, as I said, called eclipsing binaries, as it says right here. And one of the things that they can be used for is you can time the and of course measure the speed that the stars are traveling using the Doppler shift. But you can time how long it takes. That's what these curves are all about right here. How much time it takes the brightness of the star to dip and then to return to normal. With that information and the speed, you can figure out how big the stars are. Which, of course, we already have an equation that describes how big stars are using their luminosity and their temperature. So you can compare those two, and this is a wonderful way to check and make sure everything is in agreement. But it's a rare situation where 2 stars are from our vantage point are exactly lined up like this. It would be nice if all the stars did this, all binary stars did this, but not all of them do, certainly. Alright, so I'll just describe that. Let's go over these. This is just kind of a summary of the chapter. So with using distance, we directly measure distance using the method of parallax. That works out to about 250 parsecs, which, it'll actually, we have actually technology now that'll allow us to go further than that. There was a spacecraft called Hipparchus that basically extends the baseline for the parallax method. At any rate, this 250 parsecs, about a little more than 800 light years. So how do we measure distances further than that? With that, we use this thing called the method of standard candles, which basically what that involves is if once we can classify the star, we know we know how what its absolute magnitude is, and once you know that, you can use the inverse square law and work backwards. We're not actually going to do the math to do this, but you've seen some of that math already with figuring out what the size of stars are. But it's using that luminosity and using the inverse square law, basically using it backwards. And it's like I said in class, it's as though, let's say that somewhere on campus there was a 100-watt light bulb. If you already knew it was 100 watts, and you could see it, and you could pick up the photons of light in your telescope, what you would do is you would figure out how much energy you're receiving, how much power you're receiving. Actually, it's power that you're interested in, which is energy per unit time. At any rate, if you got that and you measured that value in your telescope, if you knew ahead of time, like I said, that it was a 100-watt light bulb, you can, using the inverse square law, you know how much energy you should be receiving. So then, of course, you receive a certain amount of energy, you record that value, and then you use the inverse square law in reverse to figure out the distance. So that's the method of standard handling. Wien's law, which we've used multiple times, allows us to measure the temperature of stars. Remember, the stars are classified. The luminosity is a measure of the star's apparent brightness. And then, once you have what's called the absolute luminosity, you can use the inverse square law. I've been saying this over and over again to figure out distance. That's called the method of standard handling. All right. We can, of course, using the spectral lines, we can figure out what the stars are made of. There's an equation that describes what the size of a star is. Not just eclipsing binaries, but any star. You can from the luminosity and the temperature, you can figure out what the size is. Of course, stars that are eclipsing binaries, you can compare this method. All right, and then of course mass. One object has to be orbiting another to get mass using the modified version of Kepler's third law. The Doppler shift gives us what's called the radial velocity, how fast something is moving either towards us or away from us. Now it could be moving at some angle, so part of the motion is towards us or away from us. And so we call that motion the radial motion. All right. Now the Hertzsprung-Russell diagram is an extremely important discovery that these two guys, Hertzsprung and Russell, made. It's sometimes called the HR diagram. You can see it was discovered, or this HR diagram was developed, if you will, over 100 years ago in 1912. And there it is. So this is really important to understand. It is the vertical axis of the HR diagram is luminosity, right? And it's absolute luminosity. And then just a reminder: absolute luminosity is the luminosity something would appear if it were 10 parsecs away, or 32.6 light years away. This axis, the horizontal axis, is the surface temperature. And you could also put, the stellar classifications like O stars, like the G stars would be right here about where the sun is, and M stars would be way over here. All right, so a couple of things about this. I only have a couple more seconds left of this video. I'll continue more on the next video.